Welcome back class. So we were learning about the Laplace transform. We learned about the different properties of the Laplace transform, that how we can actually use the Laplace transform for the complex functions, then how by using those properties we can easily calculate their respective Laplace transform frequency domain. So if you remember the differentiation property, like if you take the Laplace transform of the derivative of a function in time domain, so we multiply with s, with f of s minus f of 0. So that was the initial condition. And also if you remember from the calculus, whenever like you go for the integrations or the differentiation, we get the initial conditions. So the calculation of the initial conditions, it's very easy using the Laplace transform. So if you want to get the, for example, the initial value f of 0 of any function, okay, for example in time domain, there is a function f of t and you want to get its initial value f of 0. So it's very easy that you get its Fourier transform, multiply it with s, and then just calculate its limit when s is approaching to infinity. So that will be equal to the initial value. That will be equal to its initial value. For example, this is a function f of s and our target is calculate its initial value. So what will we do? We will just place s approaches to infinity here. Okay, so if you directly put infinity here, so it will become indefinite form, infinity over infinity. So what will we do here? Okay, we will try to make it simplify. Okay, how we can make it simplify? This is s plus 1 square, so this will be s square plus 2s plus 1. Now here if I take the s square common, so it will be 1 plus 2s over s square. Also in the denominator, if I take x square common, it will be 1 plus 2s over x square plus 1 over x square plus 25 over x square, and the limit s approaches to infinity, or limit s approaches to infinity, this will be cancelled out. So this will be 1 plus 2 over s, okay, 1s will be cancelled, 1 plus s will be cancelled, 2 over s plus 1 over s square plus 25 over s square. Now if you put limit s approaches to infinity, so this will be infinity, this will be infinity, this will be infinity, this will be infinity. So 2 over infinity, 0, 0, 0, 0, 1 over 1, 1. So initial value is 1 for this case. Similarly, if you want to calculate the final value, okay, so solve this, s approaches to 0, s times f of s, so that will give you the final value of that case. So this is one example, you can solve this. Convolution property, a very important property, as like the Fourier transform property, that if you have time domain function, you have an impulse response. If you want to calculate the system response, so we know that the convolution is this. So if you go to the, if you take its Laplace transform, and then if you take its Laplace transform, so they are convolving in time domain, in frequency domain, they will be multiplying. Okay, or from where we can calculate the transfer function, output our input. Okay, so the calculation of the transfer function is very easy in the frequency domain, and if you know the transfer function, you can calculate the system response for any kind of the input. Okay, this is the table of the linearity examples. Okay, Laplace transform, the different pairs for the Laplace transform. Okay, so let's solve one example for the calculation of the convolution property. Okay. For the case of the simple case, so for example, if we have an electrical circuit, then how we can calculate its transfer function. Okay, let's take this example. Okay, we have and this is our input, this is the current, and this is the output in this case. Okay, here we are measuring the output. So output in this case will be input plus R times I of t plus L times of di of t over dt. So if we take its Laplace transform, this will be V of s, and basically output will be equal to the voltage drop here. Okay, the input. Okay, so the input will be equal to the voltage drop across the circuit. Okay, the voltage drop here and voltage drop across the inductor. So this will be the Laplace transform of this one. So R times I of s plus L. So what is the properties of the differentiation? S times I of s, right? So in this example we are assuming that our input is this signal and our output is current. Okay, not this output voltage drop, this output is the current. So the transfer function, that will be the output, our input. Okay, so from this V I of s, if I take I of s common, so that will be R plus SL, and the ratio of the output our input. Okay, the ratio of the output our input, that will be 1 over R plus SL. Okay, so that will be the transfer function in this case. So this way we can calculate the transfer function for any kind of the system. Okay, so that is the end of this part of the lecture. Thank you very much for your time here. There is a part about the properties, so let's quickly review this. So we know that any LTI system, we can write them in the form of the transfer function. Okay, like we have just tried 1 over s plus RL. Okay, let's say this is one transfer function. So we have s and we have a constant here. So similarly we can get denominator and denominator functions. Okay, so in a general form we can write them like this one. Okay, so the root of this, okay, if you put b of s is equal to 0, okay, the roots of this, these are called zeros, and the root of this polynomial, they are called as poles of the function. Okay, so if we want to check about the properties, so if your transfer function is a constant, that will be a memoryless system. Okay, and if you want to check the causality properties is if your input system is 0. Okay, like if your input is 0 for t less than 0, your system will be causal. Okay, and the stability property is that if you are supplying a stable input, you will get the stable output. Okay, so we can quickly check using the poles of the function. For example, if you just plot the poles of the transfer function, and if they are in left hand side plane, this is called left hand side plane, this is called right hand side plane. So if your poles are in the left hand side plane, your system will be stable. Invertibility, that if there is a function whose inverse exists like this, and if you multiply both of them, you will get the same one. Okay, like the amplifier case, so your system will be invertible. Okay, so this is one example which we will solve during the live session. That is the end of this part of the lecture. Thank you very much for your time here.